Our project is Machine OChem, which we worked on with our mentor, Dr. Cody Aldaz. To start off, let's talk about what organic chemistry is and why it's important. Organic chemistry is the study of carbon-containing compounds and their reactions. Carbon is an essential element because of its ability to form stable bonds with many elements, including itself. These are some common organic molecules that you might recognize. As you can see from these pictures, organic chemistry is all around us, from medicine to solar energy to the foods we eat to plastics. It's even used in cosmetics as well as farming, so it plays an important role in our life. And in order to create the molecules that are necessary to make these products, chemists need to perform reactions, which are made up of elementary steps. An elementary step is one step in a series of simple reactions that show the progress of a reaction at the molecular level. Here is an example of an elementary step. This is a substitution reaction where the bromine does a backside attack and displaces the water. This all happens in one step. Elementary steps are like words, and mechanisms are like sentences. For example, the Fischer-Oxazole synthesis is a mechanism. It is a sentence. The ones highlighted in orange, such as electrophilic addition to nitrile, those are elementary steps. These are the words that make up the sentence. They are the elementary steps that make up the mechanism. So what does that look like? Here you can see a picture of the mechanism and the steps listed on the side. Each step follows one another until we get our product, just like how each word following one another results in a sentence. Looking at the diagram, it seems really simple. Step 1 goes to step 2, goes to step 3, and so on. But in reality, it's really difficult to do. Right now, even with advanced technology, the steps for chemists to model a mechanism are still hard and tedious. First, we'd have to choose an elementary step to investigate and create a model of the initial and final structures. Then we have to align the molecules and run a calculation. If it works, then yay! But a lot of errors could happen along the way, such as incorrect structure or incorrect alignment. We'd have to go back and redo those steps and run the calculations again and see if it works. And if it still doesn't work, we'd have to go back and redo them again and again and again. And even if the calculation was successful, there could be more than one pathway. So we'd have to return to the beginning and investigate another elementary step and start the whole process again. There can even be multiple competing mechanisms depending on the conditions. So as you can see, it can take an extremely long time just for one small step. Say you're trying to create a new kind of medicine that can save countless lives. Imagine how long it would take if we kept using this method. Is there a more efficient way to do this?
The focus of our research is to train a computer to do organic chemistry. Our role in the project is to develop a dictionary of elementary steps in order to map out reaction pathways. So as we teach the computer more elementary steps, it'll be able to describe more chemical reaction mechanisms. This is an elementary step reaction template for tetrahedral elimination of a carbamate ester. As Vivian mentioned earlier, an elementary step is one step in a series of simple reactions that show the progress of a reaction at the molecular level. So each template applies transformations to a reactant molecule. These transformations can include deletion, or a single bond, or a double bond, aromatic, triple bond, or a difference in charge. So after the bonds are rearranged, the product of the elementary step reaction is formed. So you might be wondering what the R groups are, and the R groups are wildcards, such that the reaction template can be applied to many types of molecules. This implies that many different molecules may undergo the same elementary step. As our library of elementary step reaction templates is developed, there will be more pathways for a reaction mechanism to take. So as Vivian mentioned before, if we think about reaction templates being words, we can think about reaction mechanisms being like sentences. So how can we combine the templates together to create a mechanism? Well, in our program, we start with the reactant molecule, and we iteratively apply templates to the molecule to produce a reaction network. This reaction network can be visualized with the reaction graph, which shows a map of the possible elementary steps necessary to transform the starting material into the product. So each little red node represents an intermediate molecule, and the edges represent a specific elementary step reaction template being applied. The yellow nodes, denoted by the 0 and 20, represent our reactants and products, respectively. Notice that there are a number of feasible pathways of elementary step reaction templates to achieve the same product. So some pathways are very efficient, and others result in dead ends. However, as you can see, this network grows very large, and we don't know which paths are good. In the future, we can train a computer to recognize the most efficient pathway to achieve the final product. So now Junrei will elaborate more on the scope of our research and explain our next steps in the project.
As shown by Daniel earlier, the reaction network is grown between reactants and products using templates. The pathway in these networks are possible ways in which the molecules can react with each other at the atomic level. These networks can be combined with quantum mechanical calculation to calculate the rate of the reaction and ultimately calculate the concentration and yield of the reaction. This is highly useful because knowing how molecules react and the expected use and rates of the reaction is important for many applications like synthesis planning, reaction scope and condition screening, and retrosynthesis planning. Here's a short 30 video for us to better visualize mechanisms in the pot. As you can see, through the breaking and formational bonds, the initial molecules are transformed into final products through a series of reactions. However, as we see previously, the networks can grow very large, and we don't know which pathway is good. Furthermore, the algorithm first requires to know what the product is, then it is able to tell when to stop growing and what pathways it should consider. Although this is still highly useful for narrowing down possible pathways, it would be much more powerful if the computer could automatically suggest the best pathway and when to stop by itself by recognizing what the product is. So, in the future, to overcome these problems, we want to train a computer to recognize the most promising pathway using reinforcement learning. In a nutshell, we will reward those reactions with higher rates and penalize those with lower rates using machine learning algorithms. That way, the computer can begin to recognize which steps it should take and which steps it shouldn't. Last but not least, we have some final acknowledgements and thank yous to make. First, we want to thank Cody, our mentor, who was there for us every step of the way. In addition, we want to thank the rest of the team, Sam, Alessio, Jane, and Todd Martinez, as well as Sophia, Marisa, and SLI for making this micro-internship experience possible. And of course, a special thank you to Phil Karch, SLI, and Stanford Science Fellowship for our scholarship funding. Thank you for listening.